So we are beginning a brand new chapter, and we are going to talk about a shape that we have never ever talked about before. More triangles.
Love that sarcasm.
More triangles.
We have told you guys you're going to learn more about triangles than you ever thought you'd care to know before. We weren't kidding.
They still keep coming back. But notice the title of this particular chapter. We're going to focus on a special type of triangle, a right triangle. Right triangles are even more unique than just any triangle. There's some characteristics that we have already learned before. There are things that you've never learned before and apply it. Notice the title also is this new word, trigonometry. Okay? You'll often hear me or Ms. Hogarty say trig. There's actually a whole course that you can take later in high school that's dedicated to trig. So we will get to that. It's a really, really cool concept. All right, now, chapter 9, we've kind of revamped the order a little bit, and I think we find that this is helpful. We start with section 9.2. We're going to end up going to 9.1 eventually, all right, just to kind of give you a heads up there. The reason why we start with section 9.2, notice the title.
You've seen this before.
Pythagorean Theorem. And I think that's why we've kind of started this way, because it's something you're comfortable with, but now we're just going to apply it. It's not just going to be what you usually see when you saw it in algebra. We're going to apply it a little bit further, okay? And we've done it a little bit in this year as well. All right, so what's the Pythagorean Theorem? Obviously, you have to have a right triangle. And it says the square of the length of the hypotenuse, so you square the hypotenuse, is equal to the sum of the squares of the lengths of the legs.
Who knew that you learned a theorem back in middle school and you just didn't even realize how important those theorems would have been?
I know. Okay. So one thing to notice, and I think some of you might, is the way that we're writing the Pythagorean Theorem looks a little different than what we saw. Normally you write it, a squared plus b squared equals c squared. Does this mean the same thing?
Absolutely. It's an equation. Two sides are equal.
Yeah, so we can do that. Now, the reason why we write it this way, it's not so much for today, but what you're going to see tomorrow, all right, is something that it's going to be more helpful, okay?
Yes.
Now, does that mean if you set up the Pythagorean Theorem and you put a squared plus b squared equals c squared, that it's going to be wrong? No. It's just when we apply it to another concept that we're going to learn tomorrow, all right? So we're going to get in the habit, try to today, just to get you there, and we're going to put the c squared first. Now, let's talk about these things. They said the square of the length of the hypotenuse is equal to. So that means c is what?
C is the hypotenuse.
And how do we know where the hypotenuse is located in a right triangle?
It should be across from the right angle, and it should also be the longest side.
Okay, so if I just give you some measurements, the longest side is always the hypotenuse,
right,
and it's across from the right angle. I like that idea because when you're finding a missing side length and you're finding the hypotenuse and you actually get that to be smaller than the two legs, there's an issue, all right? So hypotenuse, make a little note. It's across or opposite the right angle, and it's the longest side, okay? Now, the other two sides, the A and B, are your two legs, and those are interchangeable. It doesn't matter which one's which. They make the right angle, all right? So, again, all of this stuff, review, recap. So this is kind of the big idea. We're going to apply this to some things and just try some basic examples to begin, and then we'll kind of work our way through it.
Yeah, you guys have seen this before, so this is definitely not new. We've done it this year, too. All right, so I've got two triangles here. We're going to start with this first triangle.
And the right triangles, keep that in mind.
And we know that because why?
There's a right angle.
Exactly. And they said we're going to find the missing side length, and then if necessary, we're going to leave our answers in radical form. Now that we've practiced simplifying radicals, we are always going to leave it as an exact answer. So we're going to be using those simplified radicals rather than decimals.
And guys, I want to stress that since this is something you've seen before, you might try these out first and then check your work with us later, all right? And again, the rounding is not going to happen unless it says so or if it's in units. And we'll kind of keep talking about that.
All right, so which side length here would be our hypotenuse?
The hypotenuse would be the one across from the right angle, so that's the unknown missing side length.
Okay, and what do you want to call it?
We'll call it C.
Call it C. Sounds great. So for our Pythagorean theorem, we're going to write what?
C squared first is equal to your A squared, so let's say 7 squared plus your B squared, which is 24. And I want to comment what Ms. Hogarty just did. She asked me first, where's the hypotenuse? Because that's the piece we have to be most cautious about, all right?
And so that's what we're going to start with.
Always a C. The A and B are interchangeable. It's the C you have to be most careful with.
All right, so if we go ahead and do a little math here, we know that C squared is equal to
49 plus 576.
Combine some like terms. We have our C squared would equal a
625.
And to get C by itself, we know we're going to
take the square root.
Now, technically, you get C is equal to a plus or minus, because we had a quadratic equation. Plus or minus what?
25.
Now, here's the thing. When we're talking about side lengths of a triangle, can you ever have a side length that is a negative number of units long?
No, so it'd just be the positive part.
So we're not going to stress out about the positive and negative stuff on our work today. I just want you guys to realize that because it is a quadratic equation, yes, that's there. The negative 25 would be an extraneous solution, so we're not going to use that. So we're just going to say C equals 25.
So you don't really need to
write
put
that
this
step.
plus or minus. But I like that she brought that up because that's actually a concept. Like some of the challenge questions we've had are been quadratic equations, and quadratic equations do technically get you two answers a lot of the times.
Yes.
So just stressing that.
Now, if C hadn't been just a side length, we would need both of those answers to be able to then determine if both of those solutions would work or if only one of those solutions would work.
Gotcha.
Okay, next one.
Hey, real quick, do you
Yes.
notice there when you found the hypotenuse, what do you notice about that length compared to the others?
Oh, yeah. That hypotenuse should be the longest side. Is it the longest side?
It is.
It is.
So we're good.
It's a good check for yourself.
Okay.
Okay, next triangle. Let's identify where's our hypotenuse.
The hypotenuse is the 13 this time.
Right. So that's what I want to start with.
That's going to be your C squared. So 13 squared equals, let's say A squared. A is the missing, so A squared plus 5 squared.
Okay?
So 169 equals A squared plus 25. So then A squared equals 140, or 144
Either
equals
way.
A squared. Sorry.
Either way.
And then, so then A equals 12. And we only want the positive amount, so that's why I have that.
And we know we just need the positive because we're talking about a side length. Love it. You guys have seen the Pythagorean theorem before. This is not new. Notice, though, that we put the C squared first. I want you guys to try to get in that habit because it's going to help you tomorrow.
Yes. And again, if you don't do that, it's not the end of the world, but it trust us. It will help more. Okay, so same directions, just two more scenarios. Again, hopefully you can try these on your own and then check with us, all right? So starting kind of like you did, we have a right triangle, so which piece is the hypotenuse?
Here, the side length of 21 is the hypotenuse because it's across from the right angle.
Okay, so that's what I'm going to start with. That's going to be your C squared, so 21 squared equals...
And let's go ahead and let's switch it up.
Okay.
Okay, so let's call the missing side here our B. So I'm going to say 9 squared plus B squared. The order of those won't matter, so it doesn't
exactly
really matter.
right.
Okay. Well, we know 21 squared is 441, and that's going to equal our 81 plus B squared. And if I go ahead and subtract an 81 from both sides, I get 360 equals our B squared. And the square root of 360 is not a pretty one, so I know I'm going to have to simplify my radical here.
Okay.
And I do see that 36 and 10 are factors of that 360.
Okay.
36 being a perfect square.
Okay.
So if I did radical 36, radical 10, I know that would give me a 6 radical 10.
Now, guys, at this point, some of you, or most of us, should be able to go straight from here to here. If you need to kind of show that, the square root of 36 times the square root of 10, that's kind of where she's coming from there.
Right.
Okay. Again,
We won't require that, but if you need it, go for it.
Yes. And again, no rounding on this, so we want an exact answer, okay? So that's this side length here. This is your 6th radical 10. Now, we didn't really talk about it on the last one, but how could we check to make sure? Because remember, the hypotenuse should still be the longest side, right?
Right.
So how could I make sure? Well, we know 21 is obviously bigger than 9. How can we make sure 21 is bigger than 6 radical 10?
Well, if I type either the radical 360 or 6 radical 10 in my calculator and get the decimal, you'll realize that that decimal value is also going to be smaller than 21.
Okay, so make sure you're checking that. I think sometimes we get an answer and we're like, oh, it works out. Like if you would put C squared equals 9 squared plus 21 squared, you're going to get a number that's bigger, which wouldn't make any sense.
Right.
Okay. All right, so in this one, which one's my hypotenuse?
The 6 radical 5 is the hypotenuse. So let's start with that. So 6 radical 5 squared. And this is one where I'll have people that make mistakes. Keep in mind it's the whole quantity that's squared.
So if I write it like kind of how she said it first, all right? What are you essentially just squaring?
Just squaring the radical 5.
So to show that we're squaring the whole thing, because this is the whole side, what would I have to have?
Some parentheses around 6 radical 5.
And do you see that happen? Mistakes being made
A lot. Cannot even emphasize how many times people goof up on that.
Okay.
So that's going to equal our, let's do a squared plus 12 squared.
And guys, if you did that, if you didn't do that, I want you to notice, if you just do 6 radical 5 squared and just square the radical 5, that's 5. So 5 times 6 is 30. If I did that, notice when I kind of end up squaring this, I subtract 144 from 30. That can't happen.
It's giving me a negative solution. That's going to be, and that won't always happen either. So you really have to just be cautious to do it correctly.
So thinking back to what we kind of explored yesterday or today, kind of looking at our radicals, when you square something that has a whole part and a radical, square both the 6 and the radical 5. So in a sense, you're squaring 6, which is 36 times 5. Okay, so what does that get you?
180. And we know our a squared and plus, it's just not liking it, 144. And if you subtract your 144, you're going to get that a squared is going to equal our 36, which that one works out nicely. That's just going to be the square root of 36, which is 6. And looking at that, we've got a 6, a 12, and a 6 radical 5. Well, that's one that it's a little bit harder to tell just by looking at that for sure that 6 radical 5 is bigger. But if you type 6 radical 5 into your calculator, you get 13.42 approximately, which is bigger than the 12, and it's bigger than the 6.
Well, and something that I often do, I know radical 5 is a little bit bigger than 2 because radical 4 is 2. So it'd have to be a little bit bigger than 2. So 6 times something a little bit bigger than 2, it has to be bigger than 12.
Yeah.
All right, so that's another way you can think of that. Now, before we move on, I want you to take notice, all right, the fact that we have some right triangles, okay, looking at the side lengths, right, we kind of arranged these two triangles on this one purposely for a reason. Notice the side lengths of this triangle and this triangle, all right? Notice kind of what you notice about the measurements, and then notice these ones, okay? Look at those side lengths. What do you notice?
Well, I noticed that this page there's some radicals, where the last one was nice because there was no radicals.
There was no
they were
radicals.
All integers.
All the sides here are whole integer numbers, okay? Now, when that happens, they have a special name for them. When that doesn't happen, because we know when you use Pythagorean theorem, you're going to have to take the square root. Not everything's a perfect square. So if you end up with side lengths that are radical form, which means that you would have to like round it if you wanted, if you had to, these are kind of a different scenario. Okay, so I'm going to have Ms. Hochgraby elaborate on that.
All right, great introduction to this. We're going to be talking about Pythagorean triples, which are going to be a set of 3 positive integers, obviously, because we're talking about side lengths. Love how I just crossed right through that. But they're positive integers. So A, B, and C are all positive integers that satisfy the Pythagorean theorem. But the important key here is that A, B, and C are all going to be whole numbers. They're integers. They're positive numbers, so they're the whole numbers. But they're those values that there's no decimals to them, so they're not going to have radicals with them either. All right? So going back to our first set of examples, give me an example of a Pythagorean triple.
7, 24, 25.
All right. So 7, 24, and 25 would be considered a Pythagorean triple. They're 3 numbers that work in the Pythagorean theorem, and we know that these work because we had already tested it. Okay? Going back to that example again, what's another set?
5, 12, and 13.
5, 12, and 13. And typically we do put them in numerical order, but honestly, as long as you've listed all 3, it doesn't really matter. All right, there's other sets of Pythagorean triples that are out there that will work in the Pythagorean theorem. And Mrs. Palermo, the very most kind of basic one that most of my kids would remember.
The 3, 4, 5.
3, 4, 5.
And again, how do we know? Because here's the deal. Just because they're whole numbers doesn't mean they're always going to work. How do I know that that's a Pythagorean triple?
Because if we put it in the Pythagorean theorem, it will satisfy that
So
theorem.
how would you show that?
So let's talk about it. Which one, if I just give you 3 side lengths, how do I know what my C, my hypotenuse
It'd be the longest, so that'd be 5.
So the question is, does 5 squared equal And it doesn't matter the order of the two. So 3 squared plus 4 squared.
So the question is, does it equal? Kind of sometimes you have to check that.
Right.
So that left side's 25, and then you get 9 plus 16, which is 25. So it does check out.
Right. This right here is a Pythagorean triple. There are lots. In fact, if you just went online and Googled Pythagorean triples, you would see a ton of them.
Like you could like double 3, 4, and 5 and say 6, 8, 10. That would be a Pythagorean triple.
That's going to also be a Pythagorean triple.
So those, you could take basically all of those and find similar ones to it.
Right. And guys, just something to be aware of. This is an important term. You're going to see this word Pythagorean triple. It might be a good test question to say, do you know a Pythagorean triple? And maybe show that it's a Pythagorean triple. Do something with that. So you're going to see this again. Make sure we know those Pythagorean triples. The important thing, they're whole numbers. They're the special cases because they don't give us weird radical answers. But those whole numbers.
So in other words, and they're also, keep in mind, the fact that they make this equation true, that means they form what kind of triangle?
A right triangle.
So again, we can't just pick any 3 whole numbers and say it works.
Right.
Okay? It has to work for the Pythagorean or the Pythagorean theorem, which means a right triangle. Okay. Let's do some more application of this. We started real basic. The stuff we've done so far, you guys have done before, okay?
Right.
So this next question says, find the area of the triangle, and then it says to the nearest tenth of a meter. So this is where we're actually going to do some rounding, all right? Now, one reason why we know is it says to do that. Another reason is notice there's units, all right? To me, and I know Ms. Hoke-Graby feels the same way here, it's more of a lodge, kind of more common sense answer. If you're given units, you're not going to say, okay, well, it's the square root of 10 meters long.
In fact, people would look at you like you're crazy if you said that.
You're going to say it's approximately this. So just kind of keep that in mind with the answers. Okay, we get a lot of those questions. How do you know when to round? Because sometimes it's not going to say. If it has units, a rounded answer is what we're going to be looking for in the end. Okay?
If there's no units, we want the exact.
Yep. Okay, so let's find the area of the triangle. Now, let's recap on how to do that. How do we find the area of a triangle?
Area of a triangle is 1/2 base times height.
So in other words, I need to know the base, which is always a side length. Okay, and notice they give you all 3 sides. All right, so how do we know which side we're going to use? Well, it depends on where the height is located.
Exactly.
Right? And notice the height. We even drew it in. The height is always perpendicular to the base. So we don't know the height.
No, we know the base is 10. So let's go ahead and let's make sure.
Okay, so that's going to be a problem. We don't know the height. Now, does that mean we can't answer this? No.
No, because I'm also seeing that really that height is forming right triangles. So I could use the Pythagorean theorem to find that height.
Okay.
Looking at just one of the halves of that triangle.
Okay. Now, one thing to notice here, and I want to stress this, is that this triangle, because they gave you these, that probably means you're going to use those side lengths. Now, notice the triangle that you're finding the area of is what kind of triangle?
It's an isosceles triangle.
And we know an isosceles triangle, obviously these are congruent.
The base angles are congruent.
The base angles are congruent. All right. And actually, in the end, these 2 triangles that formed are congruent. And we could prove it by, if you think about it, you could do angle, angle, side. You could do HL, because they share a side. Either way, because these triangles are congruent, what does that mean about the pieces that make up the base?
That they're each going to have to be 5. Because they're congruent.
Because they're going to be congruent pieces. So just something, this is a pretty common question, all right? In an isosceles triangle, the height actually also is, in a sense, a perpendicular bisector, all right, to that base. Now, does that mean every height's going to be a perpendicular bisector? No, it's just the one that goes to the side that's not congruent, okay? So I like your idea, because if we got to find the area, we got to find the height. And the only way to do that is to kind of think about, notice here, you have a right triangle, all right? And you know, that's something that's going to be a big part of this whole chapter. So let me kind of look back here. So you're going to be looking for those right triangles a lot of times. So which piece of that right triangle is the hypotenuse?
The 8. So let's start off with the 8 squared is equal to h squared plus 5. I know you just started with
That's okay.
H squared plus 5 squared. You could have said 5 squared plus h squared.
It doesn't matter. Exactly.
So 64 equals our h squared plus 25. And that's going to give us a 39.
Now, real quick, just a side note here, guys. Notice how we're using H. Yes, you could use A or B, but be careful. I've had people use A and then think it's the answer because you're saying find the area. All right? Be very careful. We haven't found the area until I find the height, and then I have to substitute in this formula. So I still got to work on this formula. All right, so I'm going to have to take the square root. Now, 39 is not a perfect square.
It is not. And it doesn't simplify either.
So should I go ahead and round it here and then use a rounded answer?
Well, no, here's the thing. If I notice that I've got a radical 39, if I leave it as a radical 39, when I go through and like put it in my formula, I may end up having to simplify that radical answer later.
Okay.
So I'm just going to leave it as radical 39.
And the other reason, guys, if you use find a rounded answer and then use that to round again, your answer is going to be a little bit off. Okay. So when it says to the nearest tenth, that doesn't mean you're rounding the height to the nearest tenth.
Right.
You're rounding the final answer to the nearest tenth. So don't round here. Okay. Leave it in radical form.
In fact, don't even worry about simplifying it.
Yeah. Unless you know it's a perfect square.
Right.
Okay.
Right.
If it said h squared equals 25, I'm going to put h is 5. So that's easy. Okay. So I'm going to put this in for the height. So area is 1/2 times 10 times the square root of 39. Now, essentially, this is basically half of 10, which is 5. And 5 radical 39 is actually the exact answer, not rounded, but it's said to the nearest tenth. So when you type 5 radical 39 in your calculator, it's about
31.2. Hang on, let me. We said tenth.
Yeah.
That's right. Okay, yeah. Usually we round to 2 decimal places, but since they just say tenth, 31.2.
And it's meters squared.
Because it's area.
Dealing with area. Okay, so this problem, again, this one wasn't just, all right, find a missing side. You had to figure out finding the height, and it didn't even say to do that. So this is one where you have to kind of think a little bit on your own. All right? These would be great test or quiz questions.
Hint, hint. All right, next one. It says find the area of the figure. Now let's first identify what kind of figure is this?
It is a trapezoid.
How do you know that?
Well, okay, so I see 4 sides, so that makes it a quadrilateral. And I see those right angles, which basically, because those sides are both perpendicular to the same side, that makes those parallel. So that 10 centimeters on top and the 10, 12, or 16 centimeters on bottom are parallel. And one set of parallel sides in a quadrilateral is a trapezoid.
All right, so we know it's a trapezoid. Now, what's the formula we learned to find the area of a trapezoid?
Okay, so area equals, all right, and there's different ways you can do it. I'm just going to do the sum of, so in parentheses, B1 plus B2 times that H all over 2.
Okay, lots of ways to write that. You could say half of the sum of the bases times the height. You could, there's lots of ways to write it. Okay. So here's what we need. We need our 2 bases. Do we have the 2 bases?
Yeah, those are the parallel sides. So that's your 10 centimeters on top and the 16 centimeters on the bottom.
Do we have the height?
No.
That's what we need. And
we're going to the height is always perpendicular to your bases. So that's the question mark. Kind of like the last one. We had to find the height.
Exactly. Now, we know that we're studying right triangles. Do you see any right triangles in this picture?
No, but, okay, here's what I'm thinking. That side, that segment that she kind of outlined earlier with where it's perpendicular to bases, if I kind of move that over to where over there, that's going to be the same distance as that. So that's the height as well, right?
Correct.
Okay, so that technically is the height. So that if we can find that, and the reason why I picked that is because I see that it formed a right triangle with that 10 centimeter side. And here's the unknown. What about the little guy down below?
Yeah.
Okay, well, the distance all the way across is 16.
Right.
And here's what I'm looking at is the other base is 10.
And what kind of a figure are you forming when you draw in that height? If I just look at this part
it's
of it,
going to be a rectangle. So the opposite sides are going to be congruent. So that's 10 centimeters. So if I take that from 16, that little piece right there is 6 centimeters.
Awesome.
Hopefully everyone sees that.
That's really good I don't know. That's a really good problem because it makes us really apply what we know about these figures. All right, and we had to find the right triangle ourselves. Now I can see that we've got this right triangle, and I'll draw it separately if it doesn't keep freezing on me. That this is going to be a 10. This is going to be our, come on now. This is the height. Oh my goodness. This is ridiculous.
That's what, it was not as bad
Height,
earlier.
and this was our 6.
Okay.
Okay. So now we can find the height, right?
Yes.
Let's
Let's
start
draw
with-
in the little right angle so I know which
Yes,
one's
definitely.
the hypotenuse.
So where is the hypotenuse?
It is the 10.
Okay.
So we'll say 10 squared equals, let's say 6 squared plus h squared. So we'll do that. 100 equals 36 plus h squared. So 64 equals h squared. That one's a nice one. So h squared, or h is 8, sorry.
All right. Now that is our
Height
that's
of,
the height.
now it's the one of that leg of that right triangle, but it's the height of the trapezoid.
So now we can put that number into the h, into the height of our formula. And now we can go ahead and find the area of the figure.
Okay.
All right, so let's do it. We know that the area is equal to, what do you get when you take 10 plus 16?
26.
So that quantity times our 8, all divided by 2. And 26 times 8, let's see.
And you could also, guys, do 26 divided by 2.
Sure you could.
Or you could do 8 divided by 2 and then multiply by 26. It's up to you.
Yeah. So if we do 208 divided by 2, that's going to leave us with an area of
104.
104. Now, this one we didn't have to worry about rounding anything.
No.
So that's nice. Keep in mind, though, this would be a case where if we had a decimal, we would want to round because we've got units here. We're talking about centimeters squared when we're talking about area.
Again, another good question to apply. It's not that basic, oh, let's just find a missing side. All right, you have to kind of look for what you're kind of doing here. All right, one more question. It says, find the value of x.
Okay.
All right, so let's find where it is first. Okay, and I notice the x is a side length of this larger triangle. Now, question, is this larger triangle, do we know if it's a right triangle?
It's not marked, so we can't assume.
And I think a lot of times people want to assume that's a right angle. All right, and the reason why I point that out is because that's one of the biggest mistakes that people make.
Definitely.
Now, the other thing to notice is they did draw in that larger triangle this altitude or height. So it probably is there for a reason. Okay?
Yeah. In fact, as I'm looking at that, I see that that really forms 2 right triangles. So even though the larger one's not a right triangle, the 2 smaller ones are right triangles.
Which means we could use Pythagorean theorem here. All right, so of the 2, the one on the right here, and I'm going to kind of outline this. Again, we know this right angle here. The reason why I outlined this one is because notice we know how many side lengths in that right triangle.
There we know 2.
2, which means we could find
The third side.
we could find this side here. So, and then we'll think about, some of you might be already thinking, oh, I know where this is going to go. So let's use what we do know, okay?
Yeah, because if I look at that other one, the x and the 6, x is unknown.
And this
6
is
I do
unknown.
know, but I really don't know exactly what that little part is. Okay, so if I did the right triangle first, the right triangle.
the right triangle.
Then
Let me
I
write
would,
that here. And here's the deal. What do you want to call this side here?
let's call it B.
Okay.
But by finding that B, then I'll know what the other part of that base would be. Okay, so let's say 10 has to be my hypotenuse there. So 10 squared equals our 6 squared plus B squared. And so I'm going to say 100 is equal to our 36 plus B squared. So when I subtract, I'm going to get a 64 is equal to a B squared. So B is 8. Okay. So if I know that that much is 8, there we go. Then
And notice, guys, this, and just going back to some vocabulary earlier, this is a Pythagorean triple.
it is a Pythagorean triple, 6, 8, 10. In fact, we talked about that one a little bit. That it was the
the-
double
It was
of
the
everything.
multiple of the 3, 4, 5.
Yeah.
Okay, so if this is 8, now why would finding this segment help us?
Because if we know that much is 8, then we know the rest of the base. If the whole thing was 12, the rest of that base would be 4.
So this piece right here is going to be 4. Okay, so how will that still help us here? Because we still haven't even answered the
So
question.
really, I'm going to have to do another Pythagorean theorem.
And
Because
the
I'm going to
reason
have to
why
find...
is because now, like you were saying earlier, she was saying, here's another right triangle. Now do we have enough information to find that missing piece?
Yes.
Okay.
So I know x is the hypotenuse. So x squared is equal to 4 squared plus 6 squared. So x squared is equal to our 16 plus 36, which ends up getting us to a 52. Now, that's not a very beautiful one to take a square root of. So we do get a radical 52. There's no units here, so we want to try to simplify if we can, which 4 and 13 are factors, so 2 radical 13.
Again, if you need to see the radical 4 times the radical 13, you don't have to show that. Now, I know, and I'm just thinking about this while we're doing all these. A lot of times people ask, well, how much work do I need to show? Okay, or, things like that. Often I know what we are encouraging is we want to see that initial setup. When you're using Pythagorean theorem, make sure you're showing us initially what are you subsing into, okay? Yeah. I know for me, a lot of times when people set it up, especially when the unknown is the hypotenuse, I know some of you can do that in your head and get straight to 52.
And that's okay.
And that's okay. But we shouldn't just see going straight here, all right? So just make sure you're providing, the one a lot of times I do is when in doubt, just show it. Okay.
Sounds good.